We're inside pump house number 4, and this is a typical well. What we have here is this concrete block is an anchor for the actual pump and motor. This is a pump discharge head, which requires a fixture between the pump itself, which is inside the well, and the motor housing. This is a 100 horsepower hollow shaft motor. The shaft goes through this motor to the pump discharge head and the pump and the casing all the way down into the well. What we have here is an air release valve, so when the pump starts, if there's any air, it captures the air and lets the air out to atmosphere so it won't have water hammer. This particular unit here is a strainer which straightens the water out to react with a water meter, so it keeps the water meter to be more accurate. This particular well is a gravel packed well. It's a large casing. It's a core approximately 24 inches with a 16-inch screen, and then it's a 12-inch well casing, and then it's a 6-inch diameter pump. This particular pump's capable of pumping 500 gallons a minute to the campus, which is over 4.5 miles, and we also have approximately 220 feet of elevation between this particular well field and our underground reservoir. So it's a large pump, and it requires approximately 180 pounds of pressure at this particular pump with one pump running to push the water to the main campus. This particular motor is in operation with a VFD, which is a variable drive unit, which we're able to speed the motor up and slow the motor down. And what happens is if we have low stream flow conditions in the river, we may want to take less water per minute and put it into the system. We do that for all the particular wells here. For one, it saves energy on the horsepower of the motor. And number two, we're able to manage what we take out of our aquifer at the same time to be in compliance with regulations and also a proper management of the water we use in the aquifer. Okay, now we went from the pumping the water through the pump. At this point, I'm at the water meter. This component here is a water meter. It takes it and sends the signals back to our work order control facility. And we have a SCADA system at the main campus that will register the pump being on or off. It will also tell me the gallons per minute and send any other alarms that's necessary for the operation of the pump. At that point, the water continues, and then we have a butterfly valve. So if we have to shut this system down, we close this particular valve, and we're able to maintain the system or take parts, dismantle the pump at this point in time. Okay, here as we continue, I have some diagrams on the wall. This particular diagram is a cutaway of a gravel packed well. It shows you the core boring into the aquifer. It shows you the screen, the stone, the pump, the well casing, and it shows you a typical well screen. And here I have a cutaway of a small scale model well screen, which happens to be, this is stainless steel well screen, and the sizing is determined on what the well field could produce. We do monitoring wells, we pump the monitoring wells down, and as we get this gallons per minute rate, the screen is sized to the well on that size. The old screens were brass, they became brittle, fell apart, required cleaning. The stainless steel is a great replacement. It's been in service for approximately 30 years. Okay, now I'm going to explain what we have here. This is a cutaway section of a pump, and what this is a vertical turbine pump. So what we have is a shaft, a water bearing. This is part of a bowl assembly, and what you're looking at here is actually a bowl assembly, and this is a pump impeller. And what this does is this forces the water up through the assembly and pushes it back to the campus. So at this point, these pumps are sized by the gallons a minute capable of the well, and also what it needs for called the TDH, which is total dynamic head, to force the volume of water back to the campus, which is the elevation and also the run of pipe. So the pump is sized by production of the well, and they keep adding different bowl assemblies to complete the motor and capability of pumping the volume. Okay, right now I'm going to explain to you, this particular pipe is a transmission pipe from our Willimantic River well field to the 5.4 million gallon reservoir, and this is a 16-inch main that's been in the ground since 1972, and it started failing at approximately 35 years of age. This particular pipe, if you can see the holes in it, the iron is deteriorated, and what that's caused from is soil conductivity between the soil and the iron pipe itself. It's an iron oxide. The iron pulls itself out of the pipe from the ground conditions, and at that point the pipe failure occurs. To replace this pipe is approximately $6 million. The university is presently in the final stages of having this pipe completely replaced. In order to prevent this failure to occur again, what we do is we poly wrap the pipe. In other words, it's like a plastic bag that the pipe sets in and seals the pipe against these soil elements. Okay, here I'm holding some bolts that come out of a water valve. But what happens is this valve is deteriorated. These bolts, this is what it should look like, and you can see the layers of deterioration, and this is caused from electrolysis as well as soil conditions. So in other words, we have stray currents. The iron picks up the stray currents, and the bolts, the metal deteriorates into the ground. And this is another big issue we have on campus that occurs, and this has only been in the ground approximately 12 years. Okay, here we have is called a gland ring. This is used on valves and different mechanical fittings. This particular item is all corroded as well, and it's from the same conditions as electrolysis and soil conditions, which ends up being a lot of money throughout a system, a lot of failures and utility outages. This particular pipe come out of our water system at the Depot campus. You can see the over 1 inch incrustation buildup, and that's buildup from iron. And today what we have is cement lined water mains, which the iron doesn't build up on the cement. In addition, that we have caustic soda for pH control. We elevate the pH from approximately 6.0 to about 7.5 range in order to stop corrosion in the pipe and also stop iron buildup. Okay, our wells are up on a plateau. It's for multiple reasons. One's a plateau is because of flooding conditions that occur. You can see that 5,100 year flood range. We have rip tides that run through the river floods that will could contaminate the wellhead. And also for wellhead protection, when you're up on a plateau, it wouldn't get contaminated from being submerged. Okay, now I'm going to try to start this pump. I'm going to turn it back in automatic and shut off automatic. I had to drop it out, so now we put it on. If you see the water out of the air valve, it's just releasing the air. The air is releasing now. At this point, you see the pressure presses up.